You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Vector indexes are specialized data structures designed to make similarity search across embeddings both fast and scalable. Embeddings, as we have seen, represent words, sentences, images, or other items as high-dimensional vectors, but their usefulness depends on our ability to compare them efficiently. A vector index organizes these embeddings in a way that supports rapid retrieval of items most similar to a given query vector. Think of a library where every book has been encoded into a coordinate in an invisible, multidimensional map. If you walk in asking for books like Pride and Prejudice, the library must instantly guide you to shelves of related novels without flipping through each title one by one. Vector indexes are the maps and shortcuts that make this process feasible, transforming embedding spaces into searchable systems that respond quickly, even when holding millions or billions of items. The need for indexing becomes obvious when considering scale. A naive similarity search would compare a query embedding against every vector in the database, calculating similarity scores one by one. For small datasets, this is possible. But for collections with millions or billions of embeddings, such as all documents on the internet or all products in a global catalog, exhaustive comparison becomes impossibly slow. Without indexing, response times would stretch from fractions of a second to hours. Users expect near-instant results, whether searching for images, retrieving legal documents, or querying support logs. Indexes solve this problem by pre-organizing the space, enabling algorithms to quickly narrow down candidate matches instead of evaluating every possibility. Indexing therefore transforms embeddings from raw potential into practical infrastructure for real-time retrieval. Similarity measures are the mathematical glue that makes vector search meaningful. Two of the most common metrics are cosine similarity and Euclidean distance. Cosine similarity measures the angle between two vectors, focusing on direction rather than magnitude, which is especially useful when embeddings are normalized. Euclidean distance, on the other hand, measures straight-line distance in high-dimensional space. To visualize the difference, imagine describing two friends by their preferences. Cosine similarity asks whether they share the same tastes regardless of intensity, while Euclidean distance also considers how strongly they hold those preferences. Both metrics have their uses, and vector indexes often support multiple similarity measures depending on the task. Choosing the right measure is critical, since it determines which neighbors are considered close and directly influences retrieval quality. Approximate nearest neighbor, ANN search, is the key innovation that makes indexing scalable. Rather than guaranteeing the exact nearest neighbors, ANN methods retrieve vectors that are very likely, though not guaranteed, to be the closest matches. This trade-off is necessary because exact nearest neighbor search is computationally expensive at scale. ANN is like searching for a restaurant. You may not find the single closest cafe in the city, but you will quickly find one of the closest, and that is usually good enough. ANN methods accelerate retrieval by orders of magnitude, while sacrificing only a small fraction of accuracy. This principle underlies nearly all practical vector indexes, making semantic search feasible in real-world systems where speed and responsiveness are non-negotiable. Hierarchical Navigable Small World, HNSW, is one of the most widely adopted AN indexing methods. HNSW builds a layered graph where vectors are nodes connected to their neighbors. At higher levels, the graph is sparse, enabling fast navigation across distant regions of the space. At lower levels, the graph becomes denser, allowing precise local search. A query begins at the top level, quickly traverses long-range links, and then descends into finer layers to locate the most similar vectors. The structure mimics how people navigate cities, first using highways to travel across regions, then local streets to reach the exact destination. This multi-level organization allows HNSW to combine speed and accuracy effectively, making it a favorite in many vector database implementations. The advantages of HNSW lie in its balance of performance characteristics. It achieves high recall, meaning it finds the correct neighbors most of the time, while also delivering low latency. Memory usage is optimized by connecting each node to a limited number of neighbors, preventing the graph from becoming unmanageably dense. Unlike some other methods, HNSW does not require aggressive quantization, which means it often retains higher accuracy. At the same time, its hierarchical design enables efficient navigation, avoiding the need to scan the entire dataset. These properties make HNSW a practical choice for applications ranging from document retrieval to recommendation systems, where both accuracy and speed matter. Inverted file index with product quantization, IVFPQ, represents another major approach to vector indexing, emphasizing scalability. IVFPQ begins by partitioning the embedding space into coarse clusters, much like dividing a city into neighborhoods. A query is first assigned to the nearest cluster, and only vectors within that cluster are considered as candidates. To further reduce storage and compute requirements, vectors inside each cluster are compressed using product quantization, which approximates high-dimensional vectors with compact codes. This two-step process drastically reduces memory usage while keeping retrieval quality acceptable. IVFPQ's design reflects a pragmatic balance. It trades exactness for efficiency, making it possible to handle truly massive datasets where raw embeddings would be too expensive to store and search. The benefits of IVFPQ are particularly evident in environments with billions of vectors. By compressing embeddings into shorter codes, IVFPQ slashes memory consumption, enabling storage on commodity hardware or within budget-limited environments. Its clustering step reduces the search space dramatically, making retrieval faster than brute force while still preserving useful accuracy. IVFPQ is therefore especially valuable for large-scale deployments where storage cost is a limiting factor, such as e-commerce catalogs, multimedia databases, or enterprise knowledge repositories. It is not always as precise as HNSW, but its efficiency and scalability make it indispensable for certain applications. Disk-based vector stores represent the industrial-scale end of indexing. While HNSW and IVFPQ often operate in memory, disk-backed systems enable storage of billions or even trillions of embeddings by relying on secondary storage. These systems are slower than pure memory solutions, but allow scale that would otherwise be impossible. Disk-based indexes often employ hybrid strategies, keeping frequently accessed data in memory while storing long-tail data on disk. The analogy here is a warehouse with frequently needed goods kept at the front and rarely used items stored deeper inside. Disk-based vector stores open the door for applications where scale is non-negotiable, such as global search engines, enterprise-wide retrieval systems, and massive recommendation infrastructures. Latency and throughput considerations dominate the design of vector indexes. In real-time applications, such as chatbots or interactive search, even a delay of a few hundred milliseconds can degrade user experience. High throughput is equally critical for enterprise-scale systems that must handle thousands of queries per second. Indexing methods are therefore optimized not only for recall but also for predictable performance under load. Engineers often benchmark indexes not just on speed but on consistency, ensuring that queries return within acceptable time bounds even at peak traffic. These considerations underscore that indexing is as much about systems engineering as it is about algorithms. Accuracy trade-offs are an inherent part of approximate indexing. By definition, ANN methods accept that some retrieved neighbors may not be the absolute closest. The question becomes whether these small losses in accuracy are acceptable in exchange for massive efficiency gains. In most real-world cases, they are. For example, a recommendation system does not need the single best movie match for a user. It only needs a set of good options, all of which are near the user's profile in embedding space. Accepting approximate results allows indexes to scale orders of magnitude further, transforming what is possible in practical deployments. Building large indexes, however, takes time. Constructing HNSW graphs or clustering for IVFPQ requires significant pre-processing, especially when billions of vectors are involved. Index build times can stretch into hours or days, depending on scale and hardware. Moreover, indexes must be updated as new data arrives, which can require partial rebuilds or incremental updates. These operational costs remind us that indexing is not a one-time effort, but an ongoing process, tied closely to the freshness of data and the needs of the application. Freshness challenges arise because embeddings themselves may change. As models are updated or retrained, embeddings for the same documents or items may shift, invalidating previous indexes. In fast-moving domains such as news or social media, embeddings must be updated continuously to capture current information. This creates tension between stability and freshness. Indexes must be stable enough for reliable performance, but flexible enough to reflect evolving data. Addressing freshness is a major engineering challenge, requiring pipelines for continuous embedding generation and index updates. Evaluating index performance involves metrics such as recall, which measures how often the retrieved neighbors match the true nearest neighbors, and latency, which measures response time. These metrics provide a balanced view of effectiveness and efficiency, guiding organizations in choosing the right method for their needs. Recall captures the fidelity of approximation, while latency reflects user experience. Evaluating indexes requires attention to both, since a system with perfect recall but poor latency is unusable, while one with low latency but poor recall may frustrate users with irrelevant results. Careful benchmarking ensures that indexing choices align with the real-world requirements of applications. Ultimately, indexing interacts closely with how data is chunked for embedding. If documents are split into chunks that are too small, indexes may become bloated with redundant vectors. If chunks are too large, embeddings may lose precision and granularity. The efficiency of indexing, therefore, depends not only on algorithms, but also on upstream decisions about data preparation. This interplay highlights the holistic nature of retrieval systems. Embeddings, indexing, and chunking are inseparable, and optimizing one requires attention to all. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Industrial implementations of vector indexing have now become standard features in modern AI infrastructure. Popular vector databases such as Pinecone, Weaviate, Milvus, and Vespa often rely on HNSW, IVFPQ, or hybrid versions that combine aspects of both. These systems are designed to handle billions of embeddings while providing millisecond-level response times, enabling products like semantic search, recommendation engines, and retrieval-augmented generation workflows. To make this concrete, imagine a global e-commerce company with millions of items across dozens of categories. Instead of manually tagging and categorizing every item, embeddings capture similarity relationships, while the vector database enables customers to instantly search by meaning. This combination of embeddings and industrial-scale vector indexes turns abstract theory into practical services that people interact with daily, often without realizing the sophistication of the infrastructure behind them. The deployment of such indexes has shifted from experimental research into the realm of essential commercial utilities. Decisions about whether to deploy vector indexes in the cloud or on-premises depend on several factors, including scale, latency requirements, and data sensitivity. Cloud-based deployments offer scalability and convenience, allowing organizations to spin up vector databases without investing in their own infrastructure. However, this raises concerns about sensitive embeddings leaving internal environments, particularly in regulated industries such as healthcare, finance, or government. On-premises deployments give organizations full control, reducing exposure but requiring heavier investment in infrastructure and maintenance. The choice is akin to deciding whether to rent space in a secure warehouse managed by experts or to build your own vault at home. Both protect your assets, but each has distinct trade-offs in flexibility, cost, and control. This decision is becoming central for enterprises that see embeddings as not just data artifacts, but sensitive intellectual property, requiring careful stewardship. The open-source ecosystem has accelerated the adoption of vector indexing. Libraries such as FAISS from Meta and Annoy from Spotify provided early building blocks for approximate nearest neighbor search, giving developers the ability to experiment with embeddings long before commercial databases emerged. Today, open-source vector databases like Milvus and Weaviate continue this tradition, offering production-ready systems that can be freely adopted, extended, or integrated. Open source democratizes access to advanced indexing techniques, allowing smaller organizations and research groups to harness methods like HNSW and IVFPQ without licensing barriers. It also fosters innovation, as communities of developers contribute improvements, share benchmarks, and adapt systems for new use cases. Just as open-source operating systems like Linux became foundational for modern computing, open-source vector indexes are becoming cornerstones of the AI retrieval ecosystem. Hardware acceleration is increasingly important for scaling vector indexes. GPUs, TPUs, and custom accelerators like NPUs can drastically speed up similarity computations, making real-time vector search possible even at extreme scales. Approximate nearest neighbor search requires repeated distance calculations, and hardware designed for parallelized linear algebra excels at these tasks. For example, an index that might take seconds to search on CPUs can respond in milliseconds on GPUs. Specialized chips are also being designed for vector operations, reflecting recognition that retrieval is no longer a peripheral task but a central requirement of modern AI. The analogy is the shift from general-purpose processors to graphics cards in gaming. Once demand reached a critical mass, specialized hardware emerged to handle the workload more efficiently. Vector search is at that same inflection point today, moving from general-purpose infrastructure toward specialized acceleration. Integration with Retrieval-Augmented Generation (RAG) has made vector indexes even more vital. In RAG workflows, a language model retrieves relevant documents via vector search before generating a response, grounding its output in factual knowledge. The quality and speed of the vector index directly shape the usefulness of the overall system. If the index retrieves irrelevant or outdated documents, the model will produce poor responses. If retrieval is too slow, the user experience collapses. Vector indexes therefore form the backbone of RAG pipelines, connecting raw embeddings to generative reasoning. Without them, language models would remain limited to the knowledge frozen at pre-training, unable to adapt dynamically to new information. Indexes thus extend the relevance and lifespan of large models, making them practical for real-world use. Sharding and distribution are techniques used to manage vector indexes that exceed the capacity of a single machine. In sharding, the embedding space is partitioned across multiple servers, with each server handling a subset of the data. A query is broadcast across shards, and results are merged into a final ranking. Distribution adds complexity in ensuring balanced load and efficient query routing, but it makes indexes capable of scaling to truly global datasets. The analogy is a phone book split across different cities. No single directory holds all numbers, but together they provide full coverage. Sharding ensures that retrieval systems remain responsive even as the number of stored embeddings grows into the billions, and distribution strategies keep the system efficient and fault-tolerant. Fault tolerance becomes a critical requirement in distributed indexes. If one shard or server fails, the system must continue operating without catastrophic data loss or performance collapse. This requires redundancy, where embeddings are replicated across nodes, and failover strategies where backup servers automatically step in if primaries fail. The design is similar to power grids. No single failure should bring down the entire system, and redundancy ensures resilience under stress. Fault tolerance in vector indexes is not just about uptime, but also about trust. For organizations depending on retrieval for customer-facing applications, even a brief outage can damage user confidence. Ensuring high availability through redundancy is therefore both an engineering necessity and a business imperative. Security implications of vector databases are gaining increasing attention. Embeddings often encode sensitive information, whether personal data, proprietary documents, or confidential records, in compressed but still recoverable form. Vector indexes must enforce access controls, ensuring only authorized users can query or modify data. They must also protect against inference attacks, where adversaries attempt to reverse engineer embeddings to reveal training data. Security for vector databases is not just about encryption and authentication. It also requires awareness of the unique risks embeddings pose as compressed representations of potentially sensitive knowledge. Enterprises deploying vector indexes are beginning to treat them with the same level of caution as relational databases containing customer or financial information. Maintenance requirements for vector indexes are ongoing and cannot be ignored. As new data arrives, embeddings must be added to the index, and outdated data must be removed or refreshed. For systems using IVFPQ, new clustering assignments may need to be computed. For HNSW, graphs must be updated with new nodes and edges. Over time, indexes may need to be rebuilt entirely to maintain performance, particularly as embedding distributions shift with model updates. Maintenance is like tending a garden. Weeds must be pulled, new plants added, and structures occasionally rebuilt. Without active maintenance, indexes degrade, retrieval slows, and recall drops. Organizations must plan not only for index construction but also for continuous upkeep. Evaluation benchmarks for approximate nearest neighbor algorithms provide a way to compare recall speed trade-offs across indexing methods. Benchmarks, such as ANN benchmarks, measure how well algorithms like HNSW or IVFPQ balance accuracy and latency under different conditions. These benchmarks matter because organizations must choose indexes not just on theoretical properties, but on empirical performance in realistic workloads. Some indexes excel in high recall scenarios, while others shine in memory-limited environments. Benchmarking makes these trade-offs visible, guiding practitioners in selecting the right approach for their needs. Just as car buyers compare vehicles on speed, fuel efficiency, and reliability, engineers evaluate vector indexes on recall, latency, and memory footprint, ensuring the chosen method matches their priorities. Energy and cost efficiency are significant considerations in index design. Running billions of similarity comparisons consumes large amounts of compute power, and inefficient indexes translate directly into higher infrastructure costs and environmental impact. Optimized indexes reduce wasted computation, minimizing both cost and carbon footprint. For global-scale deployments, these savings can be immense. Energy efficiency has become not only a technical optimization, but also a corporate responsibility, as organizations face pressure to reduce the environmental impact of AI systems. Vector indexes as core infrastructure are increasingly seen through this dual lens of efficiency and sustainability. Hybrid indexing approaches are emerging to combine the strengths of different methods. For instance, a system may use IVF clustering to narrow the search space, and then apply HNSW within clusters for higher precision. Other hybrids combine quantization for memory savings with graph-based navigation for accuracy. These hybrid designs reflect the recognition that no single method is best across all dimensions of recall, speed, memory, and scalability. By layering methods, engineers can fine-tune trade-offs to match application requirements. The future of indexing is therefore less about single algorithms and more about integrated systems that blend techniques for optimal performance. Research directions in vector indexing are pushing toward adaptive and learned indexes that evolve dynamically with data. Traditional indexes are static structures built by hand-engineered algorithms, but learned indexes aim to use machine learning itself to optimize retrieval. These systems could adapt as data distributions shift, reorganizing embeddings automatically to maintain efficiency and accuracy. Adaptive indexes might even anticipate queries based on historical patterns, reorganizing storage to reduce latency. This shift parallels trends in databases more broadly, where machine learning increasingly augments traditional systems. If successful, learned indexes could make vector search not only efficient but self-optimizing, reducing the need for manual maintenance. Applications of vector indexes extend far beyond text. Image search engines rely on indexes to retrieve visually similar pictures based on embeddings from vision models. Audio search uses embeddings to identify songs from short clips or detect anomalous sounds in industrial settings. Multimodal search combines modalities, enabling queries like "Show me pictures that match this caption," or "Find videos similar to this sound and description." In each case, vector indexes provide the infrastructure that makes embeddings usable at scale. Without them, the promise of embeddings would remain trapped in high-dimensional vectors, impractical to exploit in real time. Indexes thus underpin not only language applications but the full spectrum of multimodal AI. The trajectory of this exploration naturally leads to the question of how data is prepared before embedding and indexing. Chunking strategies, how documents are split into smaller pieces before embeddings are created, directly affect index efficiency and retrieval quality. Chunks that are too large may dilute meaning, while chunks that are too small create bloated indexes with redundancy. The next episode will explore how chunking shapes the performance of retrieval systems, demonstrating that the journey from raw data to usable AI applications requires careful attention at every step. Chunking strategies, embeddings, and vector indexes form a pipeline where each stage amplifies or constrains the effectiveness of the next, making them inseparable components of modern retrieval infrastructure. In conclusion, vector indexes are the practical enablers of large-scale semantic search. Methods like HNSW and IVFPQ, supported by disk-based and distributed implementations, balance recall, latency, and memory to make real-time retrieval possible at industrial scales. They underpin applications across text, vision, and multimodal domains, while raising challenges of security, maintenance, and sustainability. The field continues to evolve with hybrid and adaptive approaches, but the core insight remains. Embeddings are only as useful as the indexes that make them searchable. By turning high-dimensional geometry into responsive systems, vector indexes ensure that I can navigate meaning efficiently, powering everything from chatbots to global recommendation engines. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.